Alright, today we're going to take a look at how we can differentiate and integrate power series. Okay, so if we have a power series for a function, then any changes we make to the function, we can also make to the series, and they'll still continue to be equal, because that's how equality works. You make one change to one thing, make the same change to the other, equality still holds. Okay, so if we take a power series, and this formula right here is just the general form for any power series. Let's say that has a radius of convergence of r greater than 0, then we know that over the interval of convergence, which is from c minus r to c plus r, we know that the function is differentiable, and the derivative and the antiderivative are going to be, as I'm showing right here. The derivative, well, you're really just using power rule. So the derivative of a sub 0, that's a constant, that's 0, so that goes away. The derivative of a sub 1 times x minus c is just a sub 1. The derivative of a sub 2 x minus c squared, we bring down the 2 and reduce the exponent by 1, and so on. And if we take the antiderivative, we get our constant. We'll put that at the front. So we have c plus, and the antiderivative of a sub 0 is a sub 0 times x minus c. The antiderivative of a sub 1 times x minus c is 1/2 a sub 1 x minus c squared, and so on. So we can apply our integral and derivative rules to a power series. Now, an important fact to understand about this is the radius of convergence when you take derivatives or antiderivatives of a power series remains the same. But what might change is the interval of convergence, meaning just those endpoints might be included or not included depending on the behavior of each function or of each series. Okay, so let's take a look at this power series. We want to find the interval of convergence for f prime, f, and the antiderivative of f. So let's take a look at f prime. Well, we can take the derivative of each of these terms, and you can see that we end up with the series 1 plus x squared plus x cubed, on, which is a geometric series. Our common ratio is x. So we know this converges when the common ratio is between -1 and 1, so when x is between -1 and 1. And we know with a geometric series, the endpoints are not included. So the interval of convergence for f prime is -1 to 1. So we know that b and c, the function and the antiderivative, are also going to converge between -1 and 1. The only thing we're unsure about is what happens at the endpoints. Okay, so let's look at the original function. Well, we already know that this converges from -1 to 1, so let's check what happens at 1. Replace x with 1, and we get the sum of 1 over n, which is the harmonic series that diverges. Let x equal -1, that's the alternating harmonic, and that converges. So the left endpoint, -1, gets included. And now the antiderivative, so we have our constant c. We take the antiderivative of each of these terms, and you can start to identify a pattern here that this is the sum from n equals 1 to infinity of x to the n plus 1 over n times n plus 1. So we check what happens when x equals positive 1, and we can tell that that converges by comparison with the p series where p equals 2. And if we let x equal -1, this converges by alternating series, so both endpoints get included.